Download this code from codegive.com, link in the description below. Unleashing Performance Superpowers with Enhanced BPF, a deep dive into Usenix ATC17. The Usenix ATC17 paper, Unleashing the Performance Superpowers of Enhanced BPF, details a significant step forward in the evolution and capabilities of Berkeley Packet Filter, BPF. This paper showcases how ebpf, extended BPF, can be leveraged beyond packet filtering to create incredibly powerful, low-overhead observability and control mechanisms within the Linux kernel. This tutorial will delve into the core concepts presented in the paper, exploring the performance gains, new features, and practical applications enabled by this technology, complete with code examples. Understanding the BPF evolution, from legacy to ebpf. Before diving into the specific innovations described in the ATC17 paper, let's briefly recap the history of BPF. Legacy BPF, CBPF initially designed as a packet filtering mechanism, CBPF allowed user space programs to specify filters that would be executed directly within the kernel's network stack. This avoided the costly context switches to user space for inspecting each packet, significantly improving performance. However, CBPF had limitations, primarily in terms of expressiveness, security, and feature set. Extended BPF, ebpf represents a major overhaul of the BPF architecture. It introduces numerous enhancements, including JIT compilation ebpf code is just-in-time, JIT, compiled into native machine code, further improving performance. A more expressive instruction set ebpf provides a richer set of instructions, allowing for more complex programs and functionalities. Map data structures ebpf programs can access and modify kernel data via BPF maps, enabling data sharing between BPF programs and user space applications. Safety verification ebpf programs undergo a rigorous static analysis process by the BPF verifier to ensure safety and prevent kernel crashes. This verification process guarantees bounded loops loops must have a known upper bound on the number of iterations. Memory access validation programs cannot access invalid memory locations. No infinite loops the program must terminate within a reasonable time. Hooks into various kernel subsystems ebpf can be attached to various kernel events, such as system calls, function entries/exits, kprobes/critprobes, tracepoints, and more. This allows for a wide range of observability and control applications. 2. Key contributions of the Usenix ATC17 paper. The ATC17 paper highlights the following crucial aspects of enhanced BPF. ebpf as a generic kernel programming framework. The paper emphasizes the shift from ebpf being solely a packet filter to a versatile framework for writing high-performance, kernel-resident programs. Performance optimizations. The paper details several optimization techniques employed to maximize the performance of ebpf programs. New capabilities and applications. The paper explores various new capabilities enabled by ebpf, along with real-world applications in areas like networking, security, and performance monitoring. 3. Core concepts and features explained with code examples. Let's explore some of the key concepts and features related to enhanced BPF, along with illustrative code snippets. Note that these examples use the BCC, BPF compiler collection, library, which provides a high-level interface for writing and interacting with ebpf programs. 1. Attaching ebpf programs to kernel events, kprobes/critprobes. Asterisk concept asterisk K probes allow you to dynamically insert probes into arbitrary kernel functions. When the function is executed, the attached ebpf program is executed. CRID probes are similar but execute when the function returns. This is a powerful mechanism for tracing function execution without modifying the kernel source code. Asterisk code example, using BCC. Asterisk explanation asterisk. Asterisk the C code, inside the program string, is the ebpf program. Asterisk include uapi/linux/trace.h provides the pt_regs structure, which contains the register's state at the time of the probe. Asterisk kprobe__do_sys_open and cridprobe__do_sys_open are special function names that tell BCC to create a kprobe and cridprobe, respectively, attached to the do_sys_open kernel function. The prefix kprobe__ and cridprobe__ are mandatory. Asterisk bpf_time_get_ns, retrieves the current kernel time in nanoseconds. Asterisk bpf_trace_print_k, is a special ebpf function that writes a formatted message to the kernel trace pipe, which can be read from user space. Crucially, bpf_trace_print_k is extremely limited in the amount of data it can print. It's primarily for debugging and should not be used for high-volume data collection. Asterisk the Python code uses the BCC library to compile the ebpf program, attach the probes, and then read and print the output from the kernel trace pipe. Asterisk running the example asterisk. 1. Install BCC, sudo apt-get install bpf cctools linux headers $, for Debian/Ubuntu. Adjust the command based on your distribution. 2. Save the code as open_tracer.py. 3. Run, sudo python 3 open_tracer.py. 4. In another terminal, execute ls. You should see output in the first terminal indicating that sys_open was called. 2. Using ebpf maps for data sharing. Asterisk concept asterisk ebpf maps are key-value storage structures that allow communication and data sharing between ebpf programs and user space applications. They are crucial for collecting and analyzing data from the kernel. The paper heavily relies on the efficient use of maps for collecting performance metrics. Asterisk code example, using BCC. Asterisk explanation asterisk. Asterisk bpf_perf_output, events, creates a bpf perf output map named events. This map uses a ring buffer to efficiently transfer data from the kernel to user space. Asterisk the data_t struct defines the data that will be collected by the ebpf program. Task_com_len is a constant defined in the Linux kernel headers. Asterisk bpf_get_current_PID_tgid, retrieves the current process ID, PID, and thread group ID, TGID. Asterisk bpf_get_current_com, retrieves the command name of the current process. Asterisk events.perf_submit, CTX, and data, size of, data, submits the collected data to the events perf output map. Asterisk the Python code defines a print_event function that is called whenever new data is available in the events map. Asterisk b events.open_perf_buffer, print_event, attaches the print_event function to the events map. Asterisk b.perf_buffer_poll, polls the perf buffer for new events. Asterisk running the example asterisk. 1. Save the code as clone_tracer.py. 2. Run, sudo python 3 clone_tracer.py. 3. In another terminal, run various commands, example ls, PS. You should see output in the first terminal whenever a new process is created using clone. 3. Using trace points. Concept trace points are static instrumentation points embedded in the kernel code. They provide a stable ABI, application binary interface, compared to kprobes, which are tied to specific kernel function implementations that can change across kernel versions. The paper would likely recommend trace points when available due to their stability. Code example, using BCC. Explanation b.attach underscore tracepoint, TP equals syscalls sys underscore enter underscore execv, fn underscore name equals trace underscore sys underscore enter, attaches the trace underscore sys underscore enter ebpf function to the syscalls sys underscore enter underscore execv trace point. This trace point is triggered when a process is about to execute a new program, example using execv. Struct trace underscore entry *ctx represents the context for the trace point. The exact structure of this context depends on the specific trace point. To understand the structure of the data available at the trace point, you'll need to consult the kernel documentation or use tools like tracecmd to inspect the available fields. For the syscalls sys underscore enter underscore exec trace point, you could find details in the kernel source code under include /trace /events /syscalls.h. However, for simplicity, the example above collects data available regardless of which trace point is used to attach the program. *bpf underscore get underscore current underscore uid underscore gid, retrieves the current user ID, UID, and group ID, gid. Running the example *. 1. Save the code as execv underscore tracer.py. 2. Run, sudo python 3 execv underscore tracer.py. 3. In another terminal, execute various commands, example ls, ps, mkdir. You should see output in the first terminal whenever a new program is executed. 4. ebpf and networking, xdp and tc. Concept ebpf can be used in the networking stack to perform packet filtering, modification, and traffic control. Two key technologies are XDP, Express Data Path allows ebpf programs to be attached directly to the network interface driver, enabling extremely fast packet processing at the earliest stage of packet reception. This is ideal for tasks like DDoS mitigation and load balancing. TC, traffic control ebpf programs can be attached to TC ingress/egress queues, allowing for more sophisticated traffic shaping, filtering, and policing. Example, XDP, using BCC. This example drops all incoming ICMP packets. Explanation include uapi/linux/bpf.h, includes definitions specific to BPF programs. Include linux/ip.h and include linux/icmp.h, includes the IP and ICMP header definitions. BPF underscore license, GPL, specifies the license for the BPF program. This is mandatory. Struct xdp underscore md *ctx, the context passed to the XDP program. It contains information about the packet. *ctx-data and ctx-data underscore end, pointers to the beginning and end of the packet data. It's crucial to check that accessing header fields doesn't go beyond data underscore end. *xdp underscore drop, tells the kernel to drop the packet. *xdp underscore pass, tells the kernel to continue processing the packet. *bpf underscore print k, is used for simple debugging in XDP programs. Asterisk running the example asterisk. 1. Save the code as xdp_drop_icmp.py. 2. Replace eth0 with the correct network interface name. You can use IP address to find the interface name. 3. Run sudo python 3 xdp_drop_icmp.py. 4. In another terminal, try to ping the machine from another host. You should see that the ping requests are not answered. 5. Press Ctrl+C to stop the program and detach the XDP program. Pinging should then work again. Important considerations for XDP asterisk. Asterisk driver support asterisk XDP requires specific driver support. Not all network drivers are XDP enabled. Asterisk XDP modes asterisk XDP has different modes of operation, such as XDP_flags_skb_mode and XDP_flags_drv_mode. XDP_flags_drv_mode is generally faster but requires more driver support. XDP_flags_skb_mode is a fallback mode that uses the standard kernel networking stack. Asterisk error handling asterisk proper error handling is crucial in XDP programs to prevent kernel panics. 5. Performance optimizations, as discussed in the paper. The ATC17 paper likely discusses various performance optimizations, including tail calls allow ebpf programs to call other ebpf programs without returning to the caller. This can significantly reduce overhead when chaining multiple ebpf programs together. This avoids pushing and popping return addresses on the stack. Read-only maps maps can be declared as read-only to the ebpf program, allowing the JIT compiler to generate more efficient code, example by caching map values in registers. In kernel aggregation performing data aggregation, example calculating sums, averages, histograms, within the kernel using ebpf can significantly reduce the amount of data that needs to be transferred to user space. The ATC17 paper likely explores these aggregation techniques for performance monitoring. Efficient map lookups choosing the appropriate map type, example hash map, array map, per CPU array map, can have a significant impact on performance. Per CPU array maps are often the fastest for collecting data on a per CPU basis. JIT compilation ensuring that ebpf programs are JIT compiled is essential for achieving optimal performance. 6. New capabilities and applications, based on paper concepts. The paper likely covers use cases extending beyond the initial packet filtering concept. Performance monitoring tools ebpf can be used to create powerful performance monitoring tools that can collect detailed information about CPU usage, memory allocation, I/O operations, and network traffic with minimal overhead. Security auditing and intrusion detection ebpf can be used to monitor system calls, file accesses, and network connections for suspicious activity. The paper likely showcases the ability to do real-time security analysis within the kernel. Dynamic tracing and debugging ebpf allows for dynamic tracing of kernel and user space functions, making it easier to debug complex performance issues. The paper likely emphasizes the lower overhead of ebpf compared to traditional tracing tools like strace or perf. Advanced load balancing ebpf can be used to implement sophisticated load balancing algorithms in the kernel, allowing for more efficient distribution of traffic across multiple servers. Container security and isolation ebpf can be used to enforce security policies and isolate containers from each other. 4. Limitations and challenges. Despite its power, ebpf has some limitations. Complexity writing and debugging ebpf programs can be complex, requiring a good understanding of the kernel and BPF architecture. Security although the BPF verifier provides strong security guarantees, vulnerabilities can still occur. Careful design and testing are crucial. Kernel version compatibility ebpf features and capabilities can vary across different kernel versions. Writing portable ebpf programs that work on multiple kernel versions can be challenging. Limited instruction set the ebpf instruction set is limited compared to a general-purpose programming language. Map size limits BPF maps have size limits. Conclusion. The Usenix ATC17 paper Unleashing the Performance Superpowers of Enhanced BPF highlighted the significant advancements in ebpf and its potential as a generic kernel programming framework. By leveraging ebpf, developers can create powerful, low-overhead observability, security, and control mechanisms within the Linux kernel. While ebpf presents challenges in terms of complexity and kernel version compatibility, its performance benefits and versatility make it a valuable tool for a wide range of applications. The examples provided here only scratch the surface of what is possible with ebpf, and further exploration of the BCC library, kernel documentation, and other ebpf resources is highly recommended. Remember to consider performance implications and security best practices when developing ebpf programs. Experiment with different map types, optimization techniques, and tracing hooks to fully realize the performance superpowers of enhanced BPF.